Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to continue our discussion in partial differential equations, and in particular we're going to turn our attention to transient problems now, initial value problems. So far we've looked at how the method of separation of variables and the corresponding method of superposition works for steady problems, and we'll see today that there, with a very small adaptation, then we can use the same technology, the same techniques to address transient problems. So let's get right to it. So this is modeling methods in ME. And we are going to be addressing time-dependent what we call transient PDEs, partial differential equations, or basically initial value problems. So the method of separation of variables may be used directly if, first of all, we have homogeneous governing equation. So basically no generation. Whether we're talking about heat, conduction, the heat equation, or we're talking about anything else that cannot be an independent term of the governing equation, we should have homogeneous boundary conditions. Whether they're first kind, second kind, or third kind, it really doesn't matter. They have to be homogeneous. And we have to have a non-homogeneous initial condition. So again, it's very restrictive because this combination has to apply, or has to be true, for separation of variables to apply directly. But if not, we'll see some tricks by which we can transform the problem into something, or a combination of problems that look like this, by using superposition and other things. So let's go straight to an example. Let's do a 1D transient heat conduction. So this is a heat diffusion equation. So the governing equation, we already formulated this equation. So in 1D, we have the Laplace of t, which is simply the t dx, assuming that one directional is just x. And x is now a function of x and t. That's why it's a partial differential equation, even though it's one dimensional. Is equal to 1 over alpha dt dt. Again, this is called the diffusion equation. And as I've mentioned before, this right now we're formulating in terms of the temperature, but the same thing would apply to the diffusion of momentum, the diffusion of species, the diffusion of energy. They all actually, well, in this case, this is diffusion of energy. They will actually will yield an equation that looks exactly like this, where this alpha right here is just diffusion coefficient, which is a combination of the physical parameters of the medium. In this case, will be a combination of the conductivity, which you know it goes here, and the density and the specific heat, which go here, and the accumulation term. So in this case, alpha is conductivity divided by density and specific heat capacity. And as you can see, it would have to have units of meters squared per second, right? In order to cancel out the units on the left and on the right. Remember that x squared has units of meter squared and time has units of second. So that would actually, and obviously temperature and temperature have the same unit. So the top cancels out, and in order to cancel the x squared and the t, it would have to have meter squared per second. So regardless of the type of physical quantity that we're diffusing, in this case temperature, the diffusivity coefficient would have to have always the same units, meters squared per second. In the case of momentum diffusivity, for example, the diffusion of momentum, the momentum diffusivity is called nu, which is also called the kinematic viscosity, which is viscosity divided by density, and it has units meters squared per second. So it always applies this way. So in this case, it's called the heat diffusivity, but the equation doesn't change if it is something else. Now we are going to establish that the initial condition at time equals 0 is some d0, which could be a function of x. Okay, so at time equals 0, we have some non-homogeneous, So it's non-homogeneous temperature distribution, which can be also a function of position. And let's say that for this particular case, the boundary conditions goes as follow. At x equals 0, we have the TDX is equal to 0. So you can see this is second kind. Is homogeneous. It basically means that the field or the domain is insulated on the left-hand side at x equals 0. Q is equal to 0. That results into this. We already formulated how these boundary conditions work. And on the right-hand side, the TDX at x equal L plus H, which is a given coefficient, times T at x equal L is equal to 0. So this is a third kind, and it's also homogeneous. So remember, second kind is called Neumann condition, third kind is called Robin condition, first kind is called Dirichlet condition. In this case, it's also called a natural condition, and this one's called convective condition, such that H is equal to the film coefficient divided by the conductivity. The film coefficient is the heat transfer coefficient in Newton's school of thought. All right, so separation of variables applies directly because all conditions apply. The governing equation is homogeneous, initial condition is non-homogeneous, and both boundary conditions, in this case we only have two because the problem is one-dimensional, is also homogeneous. So let's see, we're going to let, as we did before, we're going to do a separation of variables, that the temperature, position, and time be equal to a function of position and a function of time called tau. If we plug this, plugging into governing equation yields x double prime of x times tau of t equals 1 over alpha x of x tau prime of t. Okay, so now it looks a little simpler than before. And x double prime of x divided by x of x is equal to 1 over alpha tau prime of t divided by tau of t. Now we use the same argument as we've used before in separation of variables. The left-hand side is a function of x, the right-hand side is a function of t, and this, the only way that this could be true is if they're both equal to a constant. And notice that I've already picked the sign for the constant. And in transient problems, this constant will always be negative. I'm going to show you what the reason for that is. There's no reason to think where do you want to form the eigenvalue problem. The eigenvalue problem is always going to be in the time direction, in the space direction, in direction x. Remember that all boundary conditions are homogeneous, so you want an eigenvalue problem in the x direction, and a negative constant of separation will accomplish that. But also, what happens is that when you solve the problem in time, see the equation that results in time looks like tau prime of t plus alpha lambda squared tau of t, there's a prime here, single prime, not double prime, is equal to 0. And you look at that equation, that is a first order ordinary differential equation that has a very simple solution. Tau of t is equal to a constant of integration e to the minus alpha lambda squared t. So it's that equation that you can solve by an integrating factor, but it's very simple because the equation is homogeneous, so the right-hand side integral is just a constant of integration. And that's what you end up with. The integrating factor is e to the minus alpha lambda squared t. Now, that is a solution to that problem. Had we picked a positive constant of integration, this would have been negative, and therefore this would have been positive here, meaning that the solution in time actually extends to infinity. If you have a positive exponential, the solution will never reach an asymptotic solution, will never settle down. You need a negative exponential for the solution to settle down. So we need negative exponential in time. Otherwise, the solution never settles down. So that's the reason why we pick always a negative. In the x direction, So we are not going to use the initial condition to try to find that constant of integration, because the initial condition is not homogeneous, so we cannot separate it, as we've explained before. In the x direction, we have x double prime plus lambda square x of x is equal to 0, subject to two homogeneous boundary conditions. One of them is a second kind condition at x equals 0, and the other one is a third kind condition at x equals L. So we know how this goes, right? This solution will be in terms of cosines and sine, but we don't need to do that. This is simply case number 4 in the table, or on the table. And that means that x of x is a cosine of lambda nx. So this is the eigenfunction. The eigenfunction. The eigenvalues go like tangent of lambda n L is equal to h divided by lambda n. So the eigenvalues, you can see those are implicit. That equation is not solvable, so you have to solve it by iteration like we shown in class. And the norm, well, the inverse of the norm from the table, because we always need the inverse, is 2h squared plus lambda n squared divided by L, h squared plus lambda n squared plus h. So this is the norm, the inverse of the norm. And the norm is essentially the integral of the eigenfunction square, and that will give you this. All right. So that means that the solution t of x and t, which is essentially x times tau, is equal to the summation from n equal 1 to infinity. Actually, 1 if you start the eigenvalue count at 1, or 0 if you start the eigenvalue count at 0. It really doesn't matter. Actually, I'm going to use 0 here. Cn cosine of lambda nx times e to the minus alpha lambda n squared t. So that is the general solution. This is general solution. Okay. So now we need to find the constant of integration c, or Cn. And for that, we're going to use orthogonality, as we did before for transient problems, for steady problems, that is. So now we're going to apply the initial condition that says that the temperature at time equals 0 is given by some given value t0, which can be a function of x, this is x, which is equal to, if you plug in t equals 0 here, notice that the exponential will disappear. It's the summation from n equals 0 to infinity of Cn cosine of lambda nx. So it's very simple. Using orthogonality, we multiply times the cosine on the left and on the right. So using orthogonality, move this away, we get that the integral from 0 to L of t0 of x times the cosine of lambda nx dx is equal to Cn times the integral from 0 to L of the cosine square of lambda nx dx. So the summation goes away because, remember, the eigenfunction times itself at different frequencies when you integrate over the domain goes to 0, except when the frequencies are the same. So this right here is the norm of lambda n, which we got from the table. So Cn will be related to the inverse of the norm. So Cn will be the integral from 0 to L times t0 cosine of lambda nx dx, and all of these divided by the norm of lambda n. And I'm going to frame this. That's the constant of integration. So depending on what that t0 is, if it's a constant, then very simply it's the integral of the cosine, which is a sine, and then you'll have to obviously use the relationship for the eigenvalues. The tangent of lambda n L is equal to h over lambda n. We've already shown that. So basically, well, let me expand on this. Cn is equal to 2 over L times, h squared plus lambda n squared. I'm writing the entire norm plus h. So the L only multiplies h squared plus lambda n squared, obviously, because h squared cannot add up to h. It's dimensionally inconsistent. Integral from 0 to L, t0 of x times the cosine of lambda nx dx. And this is the final form. And that goes into the summation from n equals 0 to infinity, Cn cosine of lambda nx and x times e to the minus alpha lambda n squared t. This is how the problem diffuses in time, and this is how it actually behaves in space. And this is a combination of cosines of all possible frequencies, and that will make up what the solution of the problem is. So it's a very simple implementation of the same method of separation of variables. Now, what would happen, let's move along, if the problem is multidimensional? So if you have a multidimensional transient problem, let's say that the governing equation looks like the Laplace of t, and t is now a function of x, y, z, and time, so full-fledged multidimensional and transient. And let's say that the initial condition happens to be non-homogeneous. So at time equals 0, we have again a t0 of x, y, and z. So some initial distribution of temperature, which could be a constant. And let's say the boundary conditions are homogeneous on all phases. Can be first, second, or third kind, but they're all 0. So homogeneous. So what we're going to do, well, you can separate this directly into t being a function of x, a function of y, a function of z, and a function of t. But one more convenient approach would be, all right, let's separate this into a function xi, that is a function of x, y, and z, and a function tau, which is a function of t. Let's separate it into space and time first, and then we do the space separation. So back into governing equation. If we plug this into the governing equation here, so we have tau of t times the Laplace of psi of x, y, and z is equal to 1 over alpha xi of x, y, and z times tau prime of t. So this basically means that the Laplace of psi of x, y, and z divided by xi of x, y, and z should be equal to 1 over alpha tau prime of t divided by tau of t. And as you can see, the left is a function of space, the right is a function of time. This can only be equal to a separation constant, and that constant has to be negative in order to yield a decaying exponential solution in time. So when you solve this in time, see, you'll find exactly the same solution. The equation is tau prime plus alpha lambda square tau of t is equal to 0, which yields a solution tau t equals a e to the minus alpha lambda squared t. Same decaying exponential solution in time. So all diffusion problems have these behavior in time. Now the solution in space looks like the following. The Laplace of psi of x, y, and z plus lambda squared psi x, y, and z is equal to 0. Now this is called the Helmholtz equation. So remember, this is called the Laplace equation. If you add a constant to it or a function, an independent function, this will be called the Poisson equation. But the Laplace plus the function itself is called the Helmholtz equation. So what do we do with this Helmholtz equation? Well, it's homogeneous, and we have a set of homogeneous boundary conditions. So then let's go real quick as to how do we do the separation of these. Again, same principle. We're going to let psi of x, y, and z be equal to a function of x, a function of y, and a function of z. And let's see how this goes. If we plug this into the equation here, we'll see, well, the Laplace is the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to c or z. So this will be plus x of x, y double prime of y, z of z, plus x of x, y of y, z double prime of z, plus lambda square x of x, y of y, z of z should be equal to 0. So that's that equation. All right. So if we divide everything by x, y, and z, we get x double prime of x divided by x of x plus y double prime of y divided by y of y plus z double prime of z divided by z of z plus lambda square should be equal to 0. And now let's start doing separation with the notion that we need eigenvalue problems in all directions, in x and y and in z. And remember that in x and y and in z, the problem is homogeneous. Therefore, we need to accomplish that. So let's start with x. X double prime of x divided by x of x is equal to minus y double prime of y divided by y of y minus z double prime of z divided by z of z minus lambda square, and we're going to use the separation constant beta square negative because we need an eigenvalue problem in the x direction. So in the x direction, so we have x double prime of x plus beta square x of x is equal to 0 plus some homogeneous boundary conditions at both ends of x equals 0, x equal L. And this will yield, depending on what case is on the table, depending on what combination of boundary conditions, first, second, or third kind, we'll have some eigenfunctions. We'll have some beta n eigenvalues. And we have some norm. Okay, so that problem is solved. What we're left with is then y negative y double prime of y divided by y of y minus z double prime of z divided by z of z minus lambda square is equal to minus beta square. So we have y double prime of y divided by y of y is equal to minus z double prime of z, z of z. And by the way, this is beta n. We already determined those are eigenvalues. Minus lambda square plus beta n square. And we're going to use this another separation. The left is a function of y, the right is a function of z. So we use the separation constant gamma square, and we make it negative because we want an eigenvalue problem in the y direction. So let's continue. I'm going really fast because we've done this several times, so all I'm doing is just reviewing the process. In the y direction, we have y double prime of y plus gamma square y of y is equal to 0 plus a set of homogeneous PDEs. Again, first kind, second kind, or third kind combination that will determine which one of the 9 possible cases in the table you end up with, which will determine which ones are your eigenfunctions. You're going to have some eigenvalues, gamma m. I'm going to use another index for that. Eigenvalues. And the norm of gamma m, depending on what combination you have. So what you end up with now is a problem in the z direction, which looks like minus z double prime of z divided by z of z minus lambda squared plus beta n squared is equal to minus gamma m squared. All right. And what I'm going to do is I am going to bring this one to the left. Z double prime of z. Move this up. Divided by z of z is equal to minus lambda squared plus beta n squared plus gamma m squared. And we're going to, since this is a function of z and this is a constant, we're going to call this entire thing minus delta square. Constant of separation minus delta square, which as you can see is related to these 3 constants. And we pick a negative sign because we want an eigenvalue problem in the z direction. Again, the problem in the z direction will look like this, which will yield solutions in terms of cosines and sines, plus a set of homogeneous boundary conditions, which will determine which one will survive, the sine or the cosine or combination of the two, and it will also determine what the eigenvalues will be. Z of z is going to be some eigenvalues. Eigenfunctions. The delta L, so I'm going to use the index L, are the eigenvalues. Well, the norm of delta L, n of delta L is the norm. Again, directly from the table. So what do? We put them all together. T of x, y, z, and time, remember, is xi times tau. Xi is a combination of x, y, and z. And now we have a summation over 3 indices. So we have the summation from n equals 0 to infinity, the summation from m equals 0 to infinity, over the summation of L equals 0 to infinity. Then we have a constant of integration, which we'll call CNML. We have eigenfunction in the x direction, indexed by n. We have eigenfunction in the y direction, indexed by m. We have an eigenfunction in the z direction, indexed by L. And we have e to the minus alpha lambda nml square t. That is the general solution. Such that lambda nml squared, which you can see here, you can solve for, is equal to beta n squared gamma m squared plus delta L squared is equal to beta n squared plus gamma m squared plus delta L squared. And the constant of integration, CNML, is found by implementing the initial condition. So CNML is equal to the inverse of norm of beta n, norm of gamma m, norm of delta L, times the integral of the initial condition T0 of x, y, and z, times the eigenfunction in the x direction, the eigenfunction in the y direction and the eigenfunction in the z direction. And we're going to do dz, dy, dx. And this will be the integral over the z limits, the y limits, and the x limits. And that's all. But again, all of these assumes that all boundary conditions are homogeneous, and therefore separation of variables was directly applicable. So, again, I ran through this because this is a pretty standard procedure. We've already done separation of variables many times, and we know how it works. It's just a matter of putting it together in the right order. Now, what if non-homogeneities exist in the governing equation and or boundary conditions? So we said that separation of variables will only apply if everything is homogeneous except the initial condition. So what we do is same thing we did before. Apply superposition and separation of variables as long as non-homogeneities are not time dependent. If you have a boundary condition that depends on time, let's say a temperature that changes as a function of time in one of the phases of the cube, or a flux that depends on time, or generation terms that depends on time, which is plausible, physically plausible, then this combination of things doesn't work. If non-homogeneities are time dependent, then we must use different methods, such as, for example, there's a few, but one that comes to mind is variation of parameters, VOP, or Green's functions. Green's functions method. So that's two cases. There's also Duhamel's theorem that can help. But see, superposition and separation of variables doesn't work. You need to do something about conditions that are non-homogeneous conditions that are time dependent. So let's look at a quick example. I'll give you a fly through this because this is something that we should know how to do. Let's say that the governing equation, this is a 1D heat diffusion with generation. And let's say that we have everything is non-homogeneous in this case. So the governing equation, let's say, is one-dimensional. So the Laplace is just the second partial of t with respect to x squared. We have a generation term, UG triple prime divided by k. Let's say it's a constant for the sake of argument. It can be a function of space. Remember, if it's a function of time, this is not going to work. We will need to do something different. And then the time derivative, the accumulation of storage term on the right hand side. The initial condition, temperature at x, 0, let's say again is some given t0, which can be a function of x. And let's say that the boundary conditions are such that on the left hand side we have the t dx at x equals 0 is equal to some a, while the temperature at x equal L is equal to some b, right? So we have a natural Neumann condition on the left, and we have a Dirichlet condition or force condition on the right, second kind and first kind. Remember, this means that the Q, the heat flux, is given at x equals 0, which is, let's say, let's not say that. So the Q, the normal heat, is given as some Q0, which means that minus K dt dx at x equals 0 times the normal vector at x equals 0, which points to the left, which is -1, is equal to q0. And therefore, if we want to make the analogy of what this A is essentially q0 divided by k. So if we're told that the slope of the function is equal to A, that means that it's simply the heat flux, whatever heat flux is being imposed on that wall, divided by the conductivity. This one is pretty self-explanatory. Temperature is equal to B. So, in order to solve this problem has non-homogeneities everywhere, we are going to apply some superposition. And in solving transient problems, superpositions always work by stating that we want some transient solution Tt of x and t plus some steady solution Ts of x. And I'm going to include only x, obviously, because this problem is one-dimensional. But if this problem was multidimensional, you'll have multiple dimensions in the steady part of the solution. So what would happen is that this Ts of x is just the equilibrium or steady-state solution. It's also called the asymptotic solution. This is what will happen when the time goes to infinity. When time goes to infinity, this term disappears. Remember, in diffusion problems, we always get that negative exponential behavior in time, and when time is infinity, a negative e to the minus infinity goes to 0. So all you have is this equation. So basically, this solution right here will contain the answer to this problem, right? But let's break it up, as we know how to break it up in superposition. So notice that Ts of t is the equilibrium or steady state or asymptotic solution. Well, you'll see that. So back to governing equation, you see that when we plug these superposition in here, we'll get the following. We get the partial of Tt of x and t with respect to x squared plus the total second derivative of Ts of x with respect to x squared plus ug triple prime over k is equal to 1 over alpha partial of Tt with respect to time of x comma t. And now we're going to break this up. We're going to let the transient problem be homogeneous. So this is going to be the second derivative of Tt with respect to x squared, this is a t here, is equal to 1 over alpha dtt dt of x comma t. And if we do that, then the steady problem will remain the second derivative of Ts with respect to x squared plus ug triple prime over k will be equal to 0. So we're taking the original problem and breaking it up in two by saying arbitrarily that this is equal to this. And if we say that this is equal to this, then there's no other choice but this to be 0. So if we combine these two, we'll satisfy the equation. All right. Where the initial condition, let's start with the initial condition here, which is Tt at x comma 0. Remember that the temperature at x comma 0 was given by this T0, right? So if we want to know what Tt is at x comma 0, it will be T0 minus Ts, minus a steady solution. Whatever that steady solution is, we need it to be able to solve for the transient solution. So it will be T0 given minus whatever Ts turns out to be the solution here. Because remember, Ts plus Tt is equal to the temperature. And at time equals 0, the temperature is equal to T0 hat. The boundary conditions then, again, remember the TdX is equal to A on the left. That means that this one, the derivative of this one plus the derivative of this one should be equal to A. And what we're going to do is that we're going to keep this homogeneous and we're going to pass the non-homogeneity to this one. Same thing at x equal L. So I am going to arbitrarily say that the derivative of tt with respect to x at x equals 0 is equal to 0, and the temperature T at x equal L is also equal to 0. And if that's the case, then the boundary conditions for the steady problems will become dt as the x at x equals 0 is equal to A, while ts at x equal L is equal to B. Okay, so we satisfy the original problem. The original problem said that the derivative of the temperature at x equal 0 is equal to A, so this one plus this one must be equal to A. And it also said that the temperature at x equal to L was B, so that means that this one plus this one is equal to B. So notice that we've actually sent all the non-homogeneous conditions over to the steady problem and kept the transient problem solvable by separation of variables. See, what we have is a non-homogeneous initial condition. Everything else is homogeneous. So let's solve the transient problem, the steady problem first. So the steady problem looks like this. The second derivative of Ts with respect to x squared plus ug triple prime over k is equal to 0, subject to this derivative of Ts with respect to x at x equals 0 is equal to A, while Ts at x equal L is equal to B. Right? So all you have to do is integrate this twice. Right? It's a very simple problem. So you get a parabolic distribution and then apply these two boundary conditions, and you'll get that Ts of x is equal to minus ug triple prime over k x squared divided by, actually what I'm going to do is I'm going to put this 2 here, 2k, x squared minus L squared, plus whatever the flux is on the left hand side, A, x minus L, plus whatever the temperature on the right hand side is. So this solution right here is the product of basically integrating this twice, leading to two constants of integration, C1 and C2, where the two constants of integration come into play or are found by implementing these two boundary conditions. So you can test that this is indeed the solution of this equation, and it satisfies both boundary conditions. So that's, I'm not going to go through the details of that. You already know how to do that. All right. What else? Now we need to solve the transient problem, but the transient problem, as you can see, is directly solvable. Now that we know the steady solution, this is what would happen at time equal infinity, right? This is the asymptotic solution of the problem given by this generation and this set of boundary conditions. And that problem will also come into play here in the initial condition of this new transient problem, Tt. But this transient problem is solvable by separation of variables. Transient problem Tt of x and t is now directly solvable by separation of variables. How? Well, let's look at the transient problem. So we have an equation that says that the second Tt with respect to the x squared of x and t is equal to 1 over alpha dtt dt, it's a function of x and t, such that the initial condition is given by t transient of x and 0 is equal to some t0 that is given, which can be a function of space, times ts of x, which we just found up here. With boundary conditions, dt transient dx at x equal 0 is equal to 0, and t transient at x equal L is equal to 0. So second kind, homogeneous. First kind, homogeneous. All right. So we go through the process of separation. Let t of x comma t be equal to some x of x, tau of tau. We find the tau solution to be exponential decaying. And at the end of the day, we find that t transient of x comma t is equal to the summation from n equals 0 to infinity of Cn cosine of lambda n x e to the minus alpha lambda n squared t. This is the general solution. Here's the eigenfunction, such that the eigenvalues are given by pi over 2L to n plus 1, and the norm is L over 2. That's for that combination of boundary conditions. So ultimately, the constant of integration Cn is 2 over L times the integral from 0 to L. The initial condition is T0 of x minus Ts of x, which this is given, this one we found, times the eigenfunction dx. And remember that the final solution, Tx of t, which is what we are asked to find, is a combination of this transient solution and this steady solution that we arbitrarily superimpose over each other to be able to address this problem. And that's it. That's how we implement separation of variables and superposition on transient problems. Okay? And again, regardless of whether you have transient or whether you have the non-homogeneity on the governing equation or the boundary conditions, it's always good practice to separate into a steady and a transient, superimpose those solutions, not superimpose those two solutions. Now let's do a final discussion into how to address wave-like problems. So this is a diffusion problem, right? Diffusion-like problem. The derivative with respect to time is a first-order derivative. That means that the problem will be exponentially decaying. That's what we expect of diffusion problems in time. They diffuse, they go away, they asymptotically decay, or exponentially decay in time. But what if you have a wave-like problem? Can we address these type of problems using the same techniques that we're learning here? Wave-like problems. Let's see. Wave-like problems could come in, or could arise in acoustics, vibrations, and electromagnetics, and optics, and many other fields, and etc. So we've already seen, for example, we've derived the electromagnetics of Maxwell's equations, and we've seen how those actually turn out. But let's say that in general we can express this equation as some Laplace of some field function eta that's a function of space and time. Remember, space can be, I'm going to say that space is a vector that can contain x, y, and z, or r, theta, z, or whatever curvilinear coordinates. And in time, we have these behavior that's second order in time, second order derivative in time. So this is the basic wave equation. Undamped wave equation, homogeneous also. Or, remember, you can have the Laplace of eta, whatever eta means, of x comma t is equal to the second derivative of eta with respect to time squared, x and t, plus some beta, the first derivative of eta with respect to t of x and t. And this is called the damped wave equation. Again, we've already derived these in this class for electromagnetics, for example, but this is the same as you will have in a vibrations problem, a multidimensional vibrations problem. Let's say, let's do that in the case of vibrations. Let's do an example where we have a two-dimensional domain, X and Y, and let's say that this goes from 0 to L in the X direction and 0 to L in the Y direction. And then we're holding eta at 0 here, holding eta at 0, holding eta at 0, and holding eta at 0. So let's say that this is a rectangular membrane. For example, imagine a drum, the top of a drum, but instead of being a circle, we have a rectangle or a square, and it's clamped on all the borders, like in a drum. This is a clamped membrane where eta is the deflection or displacement. So we don't allow any displacements on the perimeter because it's clamped. And then what happens when we intervene here? Okay, with an initial condition, either an initial deformation, we hold it at a non-equilibrium point, or an initial deformation or an initial velocity, for example. We tap it with an initial velocity. So the governing equation for these is c squared times the Laplace of eta, which is d second eta dx squared plus d second eta dy squared, is equal to d second eta dt squared, assuming that there's no damping coefficient. Everything is, this is an undamped wave equation, which is a function of x, y, and t. All right, with initial conditions, eta of x, y, and 0 is some given eta 0 of which could be a function of x and y, and the eta dt at x, y, and 0 is some initial velocity v0, which can also be a function of space. And let's say in this case the boundary conditions are that eta at x, y, and t for all boundaries is equal to all boundary gamma is equal to 0. So at x equals 0, at x equals L, y equals 0, y equals small l. All right, so this problem, as you can see, is homogeneous, and the governing equation homogeneous in the boundary conditions, all first kind in this case, and non-homogeneous in the initial conditions. So non-homogeneous, so this is homogeneous, and this is non-homogeneous, and this is homogeneous. So it looks like separation of variables will apply directly. The c squared, obviously in this case, is not the speed of light. That would be in the electromagnetic equations. In this case, c squared contains some physical properties of the material itself, the membrane, the material, the elasticity of the membrane, and so on. That's irrelevant now. It's a physical quantity. For us, it's just a mathematical parameter, so just keep it that way. So, because the problem is homogeneous except in the initial conditions, even though there's two initial conditions, that's okay. Separation of variable applies directly. So we're going to let eta of x, y, and t be equal to some w of x, y. So the same thing we did with the xi and the tau. So now the governing equation looks like c squared Laplace of w of x and y divided by w of x and y. Notice we're not doing a superposition, we're doing separation of variables directly. And on the right hand side, tau double prime of t over tau of t. And we are going to separate this into, with the separation constant omega, we're going to make it negative. Not because we want a decaying solution in time. This will not have a decaying solution. This will have solution in terms of cosines and sines. It's because we want eigenvalue problems in the x and y direction, because all the problem is homogeneous in the x and y direction. So in x and y, the problem that we're going to face is the Laplace of w plus omega w of x and y is equal to 0. So this is a Helmholtz equation. Well, the problem in time will be tau double prime of t plus omega square tau of t is equal to 0. Now, knowing that the problem in x and y will have these plus homogeneous condition, this will yield a solution w of x and y is equal to sine of beta nx sine of lambda my. So these are eigenfunctions in the x and in the y. Remember, you will have to break up w into x times y. Same thing that we did earlier in this class, in the same lecture. And pi over L, lambda m is m pi over small l. And in the tau direction, the solution to this problem is a cosine omega t plus b sine omega t. Such that omega nm square is equal to c square. Oops, sorry. That physical parameter is part of the equation. Again, is connected to the elasticity of the material of the membrane and some physical combination. So these wavelength omega nm, in this case not wavelength, this is a frequency, is c square times the eigenvalues in the x and in the y direction. All right, where then the general solution for the displacements of the membrane is a function of space and time is equal to the summation from n equal 1 to infinity. I'm starting the summation at 1 instead of at 0 because I know that the first eigenvalue is 0 and the first eigenfunction is 0, so it will go away. Now we have two constants of integration, cosine omega nmt plus b nm times the sine of omega nmt times the sine of beta n x times the sine of lambda my. And this right here is the general solution. And again, I skipped a lot of the detail, but you can go through the process of solving for w by replacing w with x and y and finding the eigenfunctions and the eigenvalues in the norm in the x direction, the eigenvalue eigenfunction in the norm in the y direction. And then the solution of these problems is simply cosines and sines. There it is. Now, in order to find a and m and b and m, then we have to use the orthogonality of the eigenfunctions. And those eigenfunctions are sine beta nx and sine lambda mx. All right, so we have to implement to find a nm and beta and b and m using the initial conditions. One that says that the deformated displacement at time equals 0 is some a to 0. Is that what we call it? Yes, a to 0 of x and y. And the other one is the speed at which the initial deformation takes place is some v0 of x and y. So if we differentiate this, the derivative of eta with respect to time, x, y, and t, is equal to the summation from n equal 1 to infinity, the summation from m equal 1 to infinity of, if we differentiate this expression with respect to time, we'll get a omega nm up front, multiplying a n m times, well, this will be negative times the cosine of, the sine. This is the sine of omega nmt plus beta nm times the cosine of omega nmt. I'm just differentiating this with respect to time. So the derivative of the cosine will be minus the sine. The derivative of the sine will be plus the cosine. Sine beta nx sine lambda my. All right. So introducing initial conditions and applying orthogonality of eigenfunctions results in the following. So basically, at time equals 0, the cosine will be 1 and the sine will be 0. So all that remains is a and m, and then we multiply times the two eigenfunctions, and a and m will come out directly out of that. So basically, a and m is equal to 1 over the norm of lambda m, of gamma m, 1 over the norm of beta n, times the integral from 0 to L, the integral from 0 to L of eta 0 of x and y, sine of beta nx, sine of lambda m y, dy dx. While beta nm is also, now in this case, 1 over omega nm, the frequency, 1 over the norm of gamma m, or lambda m, 1 over the norm of beta n, the integral from 0 to L, the integral from 0 to L, the velocity, the initial velocity, times the sine of beta nx, the sine of lambda my, dy dx. And knowing that, in this particular case, because all boundary conditions were homogeneous, the norm of beta n is 2 over L, while the norm, or the inverse of the norm of lambda m is 2 over small l. So all these boundary conditions were first kind. This is what the integral of the eigenfunction squared. This is the integral of the sine of beta nx squared, and this is the integral of the sine of gamma m y squared, or the inverse of that. And that's it. So now we have the general solution, right, in terms of these integration constants, which are infinite of them, and this infinite summations. And these are the two constants of integration. And you plug that in, and you'll have the motion of that membrane in time and in space as a result of the undamped wave equation that governs the behavior of these elastic problems or vibrations problems. So that's it. This is, again, an introduction of how you go about implementing the method of separation of variables and superposition to transient problems, both diffusion-like and wave-like problems. So what we'll see next time is how do we address this type of problems when conditions do not allow for these implementations. So when we have transient boundary conditions, or in general, geometries that are not framed in an orthogonal coordinate system, not separable. So we have to resort to numerical techniques, and that's what we're going to do next class. Thank you for your attention, and I'll see you.